Hey there everyone, welcome back to another video. Today we'll be looking at IGCSE Chemistry, CIE, and Chapter 1, States of Matter. Today we'll be looking at solid, liquids, and gases, kinetic theory, the states of matter, pressure and temperature in gases, and diffusion. So let's start. Oh, okay, let's go. Solids, liquids, and gases. Let's look at solids first. Solids have a fixed volume and shape, and they have a high density. The atoms vibrate in a fixed position but cannot change their location. Their particles are packed very closely together in a fixed and regular pattern. Liquids. Liquids also have a fixed volume but adopt the change of the container. They are generally less dense than solids. An exception is water, but much denser than gases. The particles move and slide past each other, which is why liquid adopt the shape of the container and also why they are able to flow freely. Gases. Gases do not have a fixed volume and, like liquids, take up the shape of the container. Gases have a very low density. Since there's a lot of space between the particles, gases can be compressed into a much smaller volume. The particles are far apart and move randomly and quickly, around 500 meters per second, in all directions. They collide with each other and with the sides of the container. This is how pressure is created inside a can of gas. Let's look at the summary of the properties of solid, liquid, and gas. So our state here is solid, liquid, and gas. So the density in solid is the highest, liquid is medium, and gas is the lowest. Arrangement, as we know, the solid is a regular pattern or a lattice. Liquid and gases are randomly arranged. Movement of particles, we know solid vibrates at a fixed position. Liquids move around each other slightly, and gases move quickly in all directions randomly. Energy of these particles, there's very low energy. In liquid, there's greater energy, and in gases, there's the highest energy. So over here we have the 2D diagram. As we can see, the solid particles are very close to each other. They all stick together, and that is when where they vibrate together. When we look at liquids, the particles can move slightly around each other, and in the gases, there's a lot of space which enables them to move everywhere. Okay, example. You can explain the differences in the physical properties of solids, liquid, and gases by referring to the arrangement and motion of particles. This is called the kinetic theory of matter. So, the kinetic theory of matter is basically the arrangement and motion of particles. As we looked here, this is the arrangement, regular arrangement, and this is the movement. So, that's basically what the kinetic theory of matter is. Let's move on to state changes. First, let's look at melting. Melting is when a solid changes into a liquid. It requires heat energy, which transforms into kinetic energy, allowing the particles to move. It occurs at a specific temperature known as the melting point. Boiling. Boiling is when a liquid changes into a gas. It requires heat, which causes bubbles of gas to form below the surface of a liquid, allowing for liquid particles to escape from the surface and within the liquid. It occurs at a specific temperature known as the boiling point. Freezing. Freezing is when a liquid changes into a solid. This is the reverse of melting and occurs exactly at the same temperature as the melting. Hence, the melting point and the freezing point of a pure substance are the same. Water, for example, freezes and melts at 0 degrees Celsius. Freezing requires a significant decrease in temperature or loss of thermal energy and occurs at a specific temperature. Moving on to evaporation occurs when a liquid changes into a gas and occurs over a range of temperatures. Evaporation occurs only at the surface of liquids where high energy particles can escape from the liquid surface at low temperature, below the boiling point of the liquid. The larger the surface area and the warmer the liquid surface, the more quickly a liquid can evaporate. So basically, if you notice the similarities between evaporation and boiling, you might when I read the thing, you might notice that we said that boiling formed below the surface of a liquid, and evaporation is formed at the surface of the liquid. Another key difference between them is that evaporation occurs over a range of temperatures, and boiling occurs at a specific temperature. So those are two main occurs at a specific temperature. So those are two main differences between evaporation and boiling, and you all have to remember that as it may come in your as it may come in your exams. Moving on to condensation. It occurs when a gas changes into a liquid on cooling, and it takes place over a range of temperatures. When a gas is cooled, its particles lose energy, and when they bump into each other, they lack the energy to bounce away again. Instead, they group together to form a liquid. Okay, so this is basically a small um, interconversion of solid, liquid, and gases. So as let me get the drawing tool here. Yeah. So as the energy increases, this shows the energy increases. So from a solid to a gas is called sublimation. From a solid to a liquid is melting. Liquid to a solid is freezing. Liquid to a gas is evaporation, and a gas to a liquid is condensation. So these are two special cases where the solid directly becomes a gas and a gas directly becomes a solid. So you can remember this as solid to gas is sublimation, and gas to solid is desublimation. Moving on, this is for extended state changes and kinetic theory. When substances are heated, the particles absorb thermal energy, which is converted into kinetic energy. This is the basic of the kinetic theory of matter. Heating a solid causes its particles to vibrate more, and as the temperature increases, they vibrate so much that the solid expands until the structure breaks and the solid melts. On further heating, the now liquid substance expands more, and particles at the surface sorry, gain sufficient energy to overcome the intermolecular forces and evaporate. When the boiling point temperature is reached, all the particles gain enough energy to escape and the liquid boils. These changes in a state can be shown on a graph called a heating curve. Cooling a gas has the reverse effect, and this would be called a cooling curve. These curves are used to show how changes in temperature affect changes of state. So let me just quickly draw. So we have two curves over here, as mentioned, a heating curve and a cooling curve. So let's draw this. So here, this like stairs going up is a heating curve, and another curve we have here is like stairs coming down. That's our cooling curve, and the stairs going up is our heating curve. Let's look at the heating curve. So at first we have our solid. This is the place where the solid is both liquid and solid at the same time. So it can be written as S, this, and X, L. So what this sign over here means that it's reversible. This process is a physical change, so it's reversible. During a state change, there is no temperature change. At this point, it is a liquid. Over here, it's a liquid and gas at the same time, so it can be written as XL, this sign, reversible sign, and then XG. And then from here onward, it's a gas. So this process is vaporization, and this shows how the temperature rise, and this shows the time taken. And I hope that should be clear. Let's look at the cooling curve. A cooling curve at the beginning, it is a gas. The gas condenses into a liquid. Over here again it becomes X, G, G stands for gas, the reversible sign, uh, and X, L, L stands for liquid. This whole thing is over here. Then again we have liquid, and then the liquid freezes into a solid. So this liquid or solid is like this. So X, L, reversible, X, S, and then as it goes down it's a solid. So this shows the temperature increase, and this shows the time taken. Okay, yeah, one more key point is that a cooling curve is like a heating curve by its mirror image. If you look at both these two curves and you put them together, you will see that it's like a mirror image. It's like this, like this, like this. like this, and then it starts like this. So till here we have our heating curve, and till here we have our cooling curve. When you join them, they are like a mirror image. That's what I was saying. Let's move on. Pressure and temperature in gases. A change in temperature or pressure affects the volume of gases. As the air inside a hot air balloon is heated up, it expands and the balloon gets bigger. This is because the volume of a gas increases as its temperature increases. As temperature increases, gas volume increases. So we can write this as temperature increases, gas volume GV also increases. The density decreases as the volume increases, so the balloon rises. This will mean that the let's density decreases. If you have a gas stored inside a container that is squeezed, the pressure increases as you decrease the volume. This is what happens in a bicycle pump. As you compress the bicycle pump, the high pressure allows you to inflate the tire. You can feel the force of the high pressure if you put your finger on the end of the pump. This is the bicycle pump, and pressure increases as volume decreases in a bicycle pump. Oh, I don't think we have the image over here. Okay, never mind, let's move on. Gases and kinetic theory. This again is for the extended. Gaseous particles are in constant and random motion. The pressure that gas creates inside a closed container is produced by the gaseous particles hitting the inside walls of the container. So these moving particles of gas colliding with each other in the container walls. So these move randomly in random direction. They hit the wall and then bounce back, and this is what creates pressure. This page 14. When we look up um, over here, they say they collide with each other and with the sides of the container. This is how pressure is created inside a can of gas. That is what I was trying to imply. Let's move on. So, an increase in temperature increases the kinetic energy of each particle. As the heat energy is transformed to kinetic energy, so they move faster. As the temperature increases, the particles in the gas move faster, impacting the container's walls more frequently. If the container's walls are flexible and stretchy, then the container will get bigger and bigger, just like the hot air balloon or any normal balloon. If the container is made smaller, then the gas particles hit the uh, wall more frequently. So when there's a decrease in volume, this causes an increase in gas pressure. So decrease in volume equals to increase in gas pressure. Guys, pay close attention to this because then this will help you in your physics as well when you'll be looking at pressure. More frequent collisions of gas molecules within the container wall. So, as we see, as this goes down, there will be less space for the particles to hit the wall and bounce back, which will increase the pressure. So, gas molecules collide with container walls. Yes. Okay, molecules collide more frequently with the container walls when the pressure is increased. Oops, sorry, we don't have the image here. Diffusion. This is the process by which different gases or different liquids mix and is due to the random motion of their particles. Diffusing particles move from an area of high concentration to an area of low concentration. Eventually, the concentration of particles is even as they spread out to occupy all the available space. Diffusion happens on its own and no energy input is required, although it occurs at a faster temperature. Okay, let's look at an experiment here. So over here we have our water molecules, and then here we have crystals of potassium manganate. So after 15 minutes we can see that the potassium manganate diffuses outside. So the concentration goes down as the position. The potassium manganate molecule diffuses the solution from a region of high concentration to a region of low concentration. So yes, this is the area of high concentration, and as we see there's no concentration of the potassium manganate, this will move outside, which will cause diffusion. Okay, so this was after 15 minutes. Okay, so after 4 hours it shows that The potassium manganate has completely dissolved in the water. So concentration of particles now evenly spread through the solution. Okay, equilibrium is reached. Yes. Diffusion and molecular mass. Okay. Diffusion, okay, this again is for extended. Diffusion occurs much faster in gases than in liquids, as gaseous particles move much quicker than liquid particles. At the same temperature, different gases do not diffuse at the same rate. Sorry. This is due to the difference in the relative molecular mass. Okay, again, you have to pay special attention to molecular mass because it will help you further in your chemistry, such as moles, and a video will be coming on that too soon. Okay, where were we? Lighter gas particles can travel faster and hence further. Therefore, the lower its relative mass, the faster gas will diffuse. This can be demonstrated in the reaction between ammonium, NH3, and hydrogen chloride gas, HCl, inside a long gas tube. Where the two gases meet, a white smoke of ammonium chloride, NH4Cl, is formed. This does not occur in the middle of the tube as you might expect, but much closer to the end of the hydrogen chloride, which molecular mass is 36.5, and the ammonia, which is NH4, its molecular mass is 17, are smaller and lighter. So as we see, these are the ammonium molecules and these are the hydrochloric gas molecules. So since their molecular mass is less than those of the HCl, they will be able to move faster, while this will move comparatively slower. And when they come and meet at a point, that is where a solution will be formed. So NH4 diffuses faster than HCl because it's lighter, yes. NH3 reacts with HCl, making the product of NH4Cl closer to the HCl end of the tube. NH3 molecules have less mass than HCl molecules, so diffuse faster. Hence, the product, a white smoke of NH4Cl, forms closer to the end where the HCl is. And that should be all for today's video. I hope you learned something new. Make sure you comment, like, share the video, and subscribe. Till then, see you in the next video.